How's it going, everyone? Welcome to the Lab 3 video. I wanted to start by just briefly apologizing for the recording quality of last week's video. I don't want to really bore you with what's going on, but basically all of the hardware that I record with is stuff that I own personally. It's not property of the college, and all of it is not of the highest quality for actually making video recordings. It's really my own personal hardware I buy in order to be good for my engineering work, which is largely related to training AI models. So this laptop that I'm recording on now, I have to use an external webcam because there is no webcam within the laptop. The audio is horrible, so I have some customization on the audio going on. And the dock cam is not compatible. I usually like to write in real time. I think that it paces well with respect to allowing you to understand what I'm doing. However, today I had to actually scan the notes that I'm going to show you beforehand, kind of similar to what I did in the video, the lecture video for this week as well. So just note that I'm going to get a new laptop, hopefully today, that mimics the one that I was using at the beginning of the semester, which was really, really nice in terms of the integrated audio and video quality. So things will get better soon. But in terms of the actual lab that you are doing in Lab 3, now that we're done with the boring part, everyone has probably fast forwarded already, just download this template to get started. And then open a new browser window and go to matlab.mathworks.com. And hopefully all of you have already done the part of setting up your actual MathWorks account beforehand. And remember that you wanted to do that with your Alamo email, because MATLAB is not a free software. And Alamo Colleges particularly has already paid the bill for you. So you want to get to this screen, this level of interface. And then what we're going to click on is Open MATLAB Online. So I'm actually going to start, before we even go into the lab, by telling you a little bit about how MATLAB works. So yours might not look exactly like this when you pull it up, but it'll probably look something like this. But just to make sure that we're all on the same page, you'll notice that MATLAB, like many kind of Microsoft products, is organized on a tab structure. So on the top you have tabs, and if you left click on Home and you go over to the panel that's known as Environment, and then drop down the menu of Layout, and then go to the 2-column default layout, we'll all be on the same page of how the things look. And really what's going on here is this white space area in the middle is what's known as the command window. The kind of blinking vertical cursor with the 2 greater than signs, that's known as the command line. And if any of you have used like a Linux operating system beforehand, or there's a variety of applications, if you're really into computers, that you might have heard the term command line before. If you have, that's great. If not, don't worry about it. Basically, just view that as a line in which we'll enter any command that we want MATLAB to execute. So what is MATLAB? We really haven't said anything about it yet. It is both an actual coding language along with an application. And we're kind of going to start kind of ease our way into actually writing code in MATLAB by just using it from an application point of view. And for us, it's just going to be a calculator. So we can go right to that command line and we can type things in that the way that we would use a standard calculator. So I could type 2 times 4. And I would type times by hitting Shift-8. For those of you that might not be familiar, MATLAB uses the character of the asterisk in order to know, or it interprets that asterisk character as knowing that you want to multiply the 2 things that are on each side of it. So notice that if I type that in and then I hit enter, MATLAB will echo to me beneath that the answer to your computation is 8. So not only can MATLAB do really simple calculations that we would expect that a basic 4-function calculator could do, like multiply, divide, and so on, it can do more complicated things as well. Like, for example, for those of you that are familiar with trigonometric functions, if you're not, that's great, but maybe you remember things like the sine function and the cosine. MATLAB's capable of doing those. The only question is, how do we tell MATLAB what we're trying to do? So MATLAB knew that that asterisk should be interpreted as multiplication. It turns out that it also knows that the letters SIN, if we put parentheses afterwards, and then pass in the actual angle that we want to take the sine of, it knows that we are trying to take the sine of whatever we're passing in. So hopefully maybe you remember that the sine of 0 is in fact 0. And we'll get into a lot more of that detail when we move on in the course. But for now, what I'd like you to focus on is, notice, type with me, CLEARALL, and keep your eye on this lower left-hand portion of the workspace. So we've been working exclusively in the command window, which is where we tell MATLAB what we want it to do. Now look over here in the lower left of this workspace. There is there's a row. If you notice, this is kind of a table-based structure. There's name, value, size, and class. There's a row that's denoted as ANS. And if I hit clear all, that goes away. So what do you think was actually going on there? Well, where do you see ANS in your user interface somewhere else? Well, you notice whenever you made a computation, the answer that was computed, like for 2 times 4, it didn't just say 8. It said ANS equals 8. So if you think back to when you've used a calculator before, remember that oftentimes it stores your last answer in memory in case you want to do it again. And that's exactly what's going on. Believe it or not, when you make a computation in MATLAB, you just defined your first variable. And that variable is the actual last answer, and it's denoted by the name ANS. If I hit the up key twice, or actually 3 times, you'll notice I can look at all my command history. So if I hit it 3 times for me, it goes back up to 2 times 4. If rather than just having that answer stored in the last answer variable, ANS, if I picked a name for a variable that I wanted to store it in. So think back whenever you used a calculator in high school, maybe you stored some actual values in variables A, B, and C. So I might choose to store 2 times 4 in a variable called A. So if you think about what's going on there, I picked a variable name. It had to be valid. We'll talk about all that later, but just trust me, today is valid. And I want to assign that variable equal to the result of 2 times 4. And as you may have expected, the equals operator in MATLAB actually performs that assignment. So if I re-execute this command, note that it's still 2 times 4, but I'm assigning the value to A. Now in my workspace, I don't have the variable ANS, I have the variable A, which is stored, and it takes on a value of 8. So MATLAB, as we mentioned, is both a application and a programming language, but you always get some understanding of what something is if you look at its name. So MATLAB actually is kind of a shorthand for matrix laboratory. It works really well. In fact, it's optimized for working with matrices. And that's why it's such a popular software package amongst the scientific computing community. Because if you think back to lecture this week, I talked about how linear algebra, or matrix algebra, is really the backbone of a lot of different engineering and scientific workflows. So because of this, MATLAB is going to be very good at storing matrices. And you might look at this, what's actually in the workspace, and say, oh, we created a variable A, its value is 8, but what does the size 1 by 1 mean? Well, think back to the lecture this week. Remember that we define the size of a matrix as M by N. So if something only had 1 row and 1 column, it would of course be 1 by 1. So that's an interesting thing about MATLAB. All of the variables that it stores them naturally as matrices. So what if we wanted to actually define, I don't know, something like a row vector? Let's try to do it. So I can just leave A in the workspace. You can clear it if you want, but I'm going to create a new variable called B, and I'm going to assign that equal to. And if you think about what a vector or a matrix is, it's a collection of numbers. So we have to tell MATLAB, hey, I'm not just going to give you one number, I'm going to give you a collection. And the way that you tell it that is coming is with that open square bracket. And I'm going to zoom in a little bit because I know sometimes on YouTube this is hard to see. I wish I could just post the Panapto links, but that is the open square bracket. And naturally, say I wanted to define a row vector with the elements 1 and 1 in there. So I'm probably going to type a 1. I'm probably going to type a 1. The question is, how do I tell MATLAB that, hey, that's not 11, this is 1, and this is 1? How do I delimit or separate the entries into the vector? And one way that I can do that is with commas. So if I enter 1, comma 1 after the open bracket, square bracket, close the square bracket, and then hit enter, notice the result that's printed out on the screen. MATLAB is telling me what I've done is define a row vector B, which contains the values 1, 1. And if you kind of look down at your workspace, note that B is of size 1 by 2. So that's a lot of the similar concepts that we were working in lecture this week. So what if I would do that same thing? So I'm going to hit the up key, and I'm going to redefine B again. I'm basically going to overwrite its value. But rather than put a comma in there, what if I put a semicolon? Think about what you think that would do. Do you think it would do the same thing? Well, that wouldn't be very efficient, right? We probably need a way, if we can create row vectors, to create column vectors. And that's exactly what the semicolon is going to do. Let's just kind of examine what happens when we make this computation. If you notice, we get a column of the actual values 1 and 1. So really what's happening there, that comma and the semicolon are what is known as delimiters. So when you enter values into MATLAB, depending on the nature of the delimiters, if they're going inside a square bracket, that tells MATLAB how to actually organize the individual values within that matrix. So the question is, those are both vectors, right? And vectors are one-dimensional examples of matrices, but how are we going to actually enter something in a matrix? Well, let me just actually show you here. And before we do that, I'm going to show you in the context of our lab. So here's the actual example of the lab that we're trying to do. Here is the example that I'm going to show you how to do. We have a 2x2 system of linear equations. Remember, a system of linear equations is just multiple equations They're linear because each variable is only raised to the first power. So when I actually want to solve these in what is known as matrix vector form using Cramer's rule, the first thing I have to do is to put it into matrix vector form. So let's actually look at that scan of that document that I was mentioning and see how that's done. So remember that when you're going into matrix vector form, the first thing that you have to do is actually write your equations in standard form. In standard form just means that all of the variables are on one side and all of the constants are on another side. You see, unfortunately, we're having issues even being able to open the document from the web, but fortunately I have a version of it here locally on my computer, of course, that I can show you. So here were the two equations and remember, this is the demo I'm doing, and then you're going to do the same thing for the next set of examples. So I took the two equations that I was given, and I noticed that they weren't in standard form. Equation 2 was, it had the x term first, the y term second, and that was set equal to a constant. So variables on the left, constant on the right. However, the first equation wasn't. It had a variable x on the left, but a variable y on the right. So I need to manipulate that and put it in standard form. I'm going to choose to move the y term to the left. If I have a plus 3y on the right side, I can move that to the left side by just subtracting 3y from both sides of the equation. And hopefully everyone is comfortable with the fact that when that is rearranged, equation 1 can be rewritten as 2x minus 3y equals minus 1. And since we used our standard algebra rules of whatever we do to one side of the equation, we do it to the other, any solution to that original equation will also be a solution to the second equation. So now that these two things are in standard form, I can go over to matrix vector form. Well, how am I going to do that? Well, remember that the way we do matrix vector form is we rewrite the system of equations as a coefficient matrix, that's here, times a column vector containing the unknowns, and that product is equal to another column vector that contains the constants on the right side of the equation. So let's, in the coefficient matrix, remember, just like we talked about in lecture this week, that the first row corresponds to the coefficients of the first equation. The second row corresponds to the coefficients of the second equation. And since I chose to arrange this in such a way that the x coefficients are going first and the y are going second, in my unknown column vector, I'll place the x first and the y below. So let's actually populate the coefficient matrix for now. In the first row, I'll have the coefficient of x, which is 2. In the first row, first column, I'll have the coefficient of x, which is 2. In the first row, second column, I'll have the coefficient of y, which is minus 3. And if you're confused here, make sure to go back and watch the lecture video on this, because I went in a lot more detail of how to set it up. In equation 2, we'll begin with the coefficient of x, which is 5. We'll move over to the second column. We'll have the coefficient of y, which is minus 2. So that is how I get my coefficient matrix. If I multiply by this unknown vector, that product is equal to the constant vector. From the first equation, the constant is minus 1. From the second, it's 3. So on the homework, you're going to be asked to rewrite a system of equations in matrix vector form. That's exactly what that means. That's what we're talking about there. So from that, we can get the necessary matrices that we need in order to use Cramer's rule. Remember that Cramer's rule for a 2x2 system expresses the unknowns as ratios of the determinants. So we need 3 matrices. We need the original coefficient matrix A, just copy it from matrix vector form. That's all that I did there. For AX, to solve for the first unknown, take the first column of the coefficient matrix and swap in the constant vector. So if you notice AX below A, the second column is the same. It's not changed. However, the first column is that constant vector. In a similar fashion for AY, since I'm solving for the second unknown, I'm going to leave the first column alone, go back to the coefficient, the original coefficient matrix, leave the first column alone, and swap out the second column for the constant vector. So again, if you're confused by that, just go back and watch the video. So the question is, how can I actually enter these matrices? And you're going to get to watch me get up actually and go grab the, again, unfortunately, because of the technology stuff, things are a little bit, not great, but that's okay. So I'm just grabbing that sheet that I wrote. That way I can look when I actually enter the matrices into MATLAB. So I'm going to clear all, just type clear all again, just to go back to a clean start. I'm also going to show you another trick. Type in CLC. That'll actually clear your command window. So in terms of what we need to do here, we're going to need to make computations involving these matrices, A, AX, and AY. So I showed you how to enter a vector, but I haven't shown you how to enter a matrix. Here's how you actually do it. I'm going to choose to name the coefficient matrix A just by using the letter A. I'm going to assign it equal to That's what the equal sign does. I'm going to open the square bracket to tell MATLAB it's going to be some kind of matrix, and then enter the elements in the first row separated by commas. So 2 comma minus 3. If you're curious where I got those from, remember that they're coming from that example that I just showed you. So when you do yours, you're probably going to want to write these matrices out by hand. Then hit a semicolon, and that's going to tell MATLAB, okay, go to a new row. So when you start to enter elements into MATLAB, it starts in the upper left position. When it sees a comma, it goes in the same row to a new column. And when it sees a semicolon, it goes back to a new row. So notice if I type 2 comma minus 3, 5 comma minus 2, and then close the square brackets and then hit enter, I actually get to see that that matrix looks exactly like what I tried to enter for A. So all that we've done here is we've defined this within MATLAB. So what I'm going to do now is define the other two matrices that I want. Remember that I need to define this augmented matrix AX. Its first row is minus 1, minus 3. Its second row is 3, minus 2. And I'm going to close that actual square bracket to tell MATLAB I'm done. I'm going to zoom out a little bit for this next one, and I'm going to show you something interesting. So if you notice, both of those two matrices are in my workspace. However, what if I entered AY, and I entered it the same way, first row 2 comma minus 1, second row 5 comma 3, I close the square brackets. What if I terminated with a semicolon? Now keep an eye on your workspace and keep an eye on your actual command window. Notice that nothing came out on the command window. However, it is stored in the workspace. And that's exactly what a semicolon does in MATLAB. If you don't want MATLAB to echo the result of the command back to you, just type a semicolon. It doesn't affect what is actually going on underneath the hood. The actual command is still executed. However, you don't actually have to see it if you don't want. So let's think about, and you'll see why that's useful later on in the course, because basically, even though you don't know it yet, it just feels like we're using this for a calculator. We're actually learning how to code. And we can take all of these commands that we're executing and we can store them in a file. And rather than executing the commands one by one, we can just execute the file. And in that case, if there's a bunch of things in there, you're not going to want to see the result of each computation individually. So how do I need to solve for my unknowns x and y? Well, notice that x is nothing more than the determinant of ax divided by the determinant of a. So wouldn't it be great if MATLAB had the capability to determine those two determinants by hand? And it turns out it does. And just like I was showing you at the beginning, how MATLAB has pre-built-in functions, the function here is det. So if I type det and then I open the parentheses, MATLAB is basically asking me, hey, what do you want me to take the determinant of? So let's pass in the coefficient matrix A. So if I pass in coefficient matrix A into the determinant, and I hit enter, notice that I get 11. The question is, well, is that the right answer? Well, yeah, that's what we got when we computed by hand. In fact, all three determinants are 11. So I'm going to do det A, det AX, and det AY. So if you notice, all of those are exactly what we computed by hand. So let's just set x equal to the determinant of AX divided by the determinant of A, and y equal to the determinant of AY divided by the determinant of A. So that's actually how you solve this using Cramer's rule in MATLAB. You just need the capability to define matrices and to take determinants. So let's actually look what we're trying to turn in for this. So if you notice, and you're going to redo this for your system of equations, but we need to include screenshots of a bunch of things. One is our coefficient matrix displayed on the command window. So since I already have that stored, all that you have to do is just retype A and then take a screenshot. So just hit print screen on this laptop. Where is it? You could do a bunch of other tools, but I am lazy, so I would just do it this way. So I'm going to open up Paint, and I'm going to take that screenshot. That's exactly what I'm looking for. But remember, you're not doing it for the example that I did. You're going to do it for this example here. Now, what we want to do next is actually see if we can find the size of our coefficient matrix. So it says use the MATLAB size function. As we mentioned earlier, the size of these matrices are actually included in the workspace. A is 2 by 2. But you can use the size function, just like any other function. You type in the name of the function, size, use a open parentheses to tell it you're going to pass something in, pass in the actual coefficient matrix A, close the parentheses, and hit enter. Then you notice you find that that is 2 by 2. So again, hit print screen, or however you like to take a snip tool of it. That's one of the problems of using Paint is oftentimes when you layer them over each other, you don't get the entire screenshot in there. So there is the size and the solution for the two variables. Basically all that I'm doing, I won't bore you, but go back and take screenshots of exactly what I computed for X and Y here. And you can show me the definition of AX and AY if you want, but you don't have to. So again, that is exactly what you're going to do. Do the same thing, not for the system of equations that I worked, but for this system of equations here. And I want to be really, really honest with you all. This is really, really tough material. Getting to be able to use a software package like MATLAB that people use in a day-to-day engineering environment for really, really important stuff at this point in your engineering curriculum, it's not common. So if you're a little bit intimidated, you don't quite know what's going on, please reach out. Happy to help you here, but really what we're trying to do is just use so basically to give you a big idea of why we did everything we did this week. Linear algebra really is the backbone of all the math that we need for engineering. Think back to week 1, we defined engineering as a discipline that went into the toolboxes of science and math in order to solve problems in the real world. Then we moved to the fact that all of these problems in the modern world are going to be solved by computing. So it's important to understand the basics of computing, how it works. We talked about how computers store numbers in a binary number system. All of you did a great job with that lab. I enjoyed looking at your Google Sheets and whatnot. And then we kind of moved into, well, how do computers actually make computations? You looked at actual combinational circuits and logic layouts and so on. And you all are turning that into day. Now it's moving into kind of actually understanding how, so if engineers use math and science to solve problems, and computing is the process of doing math, and we kind of understand a little bit of how a computer works. Now let's actually transition into what underlying math engineers need to do. And it turns out linear algebra is very important to that. This is also going to enable us to work with the actual mechanical engineering module in the course. And believe it or not, what you're really doing when you're starting to write those commands is to get some exposure to coding. So if you haven't had a chance to code before, you are actually doing it now, whether you know or not. And by the end of the semester, we'll use MATLAB in order to write to solve some simplistic coding challenges within our Intro to Software Engineering module. So if you have any questions, please feel free to reach out, and I'll talk to you all soon.